Hello everyone, my name is Kathan and today we'll be discussing the problem maximum subarray sum from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. We are given an array of n integers. Our task is to find the maximum sum of values in a contiguous non-empty subarray. Now what is a subarray? It's, you can say, the contiguous segment in an array. Now there is one more thing which is called subsequence. A subsequence is actually formed by removing one or more elements in the array, right? So not necessarily contiguous, but a subarray is a contiguous segment of the array. Fine, so you cannot skip elements in that segment. Then put first line has an integer n, the size of the array, and the second line has n integers x1, x2, so on till xn, the array values. The interesting thing is, if you see, n is as high as 10 power 5, fine, but the xi goes from minus 1e9 to plus 1e9. Now this is, you can say, the approximate range of the integer data type, and like you can clearly see that if all the values are positive, all the values are 10 power 9, the maximum subarray sum, or you can say the segment with the maximum sum, will be the array itself, and that sum will be actually 10 power 9 to 10 power 9, which is 10 power 18, which is very well higher than the integer range. So you should actually use long data type to store the maximum subarray sum. And like in the output, you have to print the maximum subarray sum. So they are not asking you that segment, they are asking you what is the sum of that segment. That is, find me a segment which has maximum sum, and they call this maximum subarray sum. It's a classical problem in arrays, so it comes a lot in interviews as well. But the idea that will be used is also great. Like it has a very reusable idea that we'll develop to solve this question. And yeah, I mean, you can see the example test case here. So n is 8 and these are 8 elements. Now of course I'll go through this test case when we look the discussion, but if you want to see what is the maximum subarray sum, this is the maximum subarray sum here. Now for this subarray, you will find that the sum is actually 9. 5 plus 3 8 plus 3 11 minus 2 9. So this is the maximum subarray sum, in the sense this is the segment which has the maximum you can say maximum sum, and that sum is actually 9, right? So we were after this segment, but we have to print the sum. So I guess the question is clear. We got 2 points out of this. We have to find out a segment which is the maximum sum, and we have to use long to store the maximum sum, right? So yeah, I mean, that's about this question. Let's go on to the iPad and discuss on how to approach this question. First things first, let's talk about constraints here. So you know that n was as high as 10 power 5, right? So order of 10 power 5. So what it says is you cannot do a order of n square solution, right? So you'll have to do either, let's say, n log n, or order of n, or log n, or maybe less than that. So this order of n square solution won't work here. If you want to do, you try finding solutions of this type. Fine. Now let's look at the example test case that was given to us to better understand how this problem can be approached. Now, what are the subarrays? Let me show you some subarrays here, so you will get an understanding of what is happening. So one subarray is this. See, one subarray is this. Then another subarray is this. So this is one subarray. The interesting thing about subarrays is all the values here will be contiguous, right? So you pick a contiguous segment out of this input array, and that will form a subarray, right? Now, if you want to see like which subarray is the maximum sum here, you will try to pick as many positive elements as possible, right? So here you can see this 3 is there, this 3 is there, 5 is there, right? So you are picking a lot of bigger guys here, and you might say, okay, there is a negative 2 here, but if I take negative 2 and this 3 together, I'll still get a gain. So it makes sense to take all of these guys together, and now this sum will turn out to be 5 plus 3 8 plus 11 minus 2 9, and this itself is the maximum subarray sum, this 9. And what is the subarray corresponding to maximum subarray sum? This subarray, right? They're not asking the subarray, but they're asking us this value 9. Okay, so how do you approach this question then? So this was very intuitive, like just looking at the example test case, you were able to figure it out that no other subarray exists. Now let's think about the brute force first, because I guess we can learn a lot from the brute force here, and maybe build up the solution step by step. Okay, so what is the brute force way to generate all the possible subarrays? That's what I'm trying to ask you. Let's see. Let's say n was some 5. So we have 5 elements. These elements are in range minus 1e9 to plus 1e9. That's also important. A1, A2, A3, A4 and A5. The brute force way would be to simply check all the subarrays, right? Just check all the subarrays and what is the sum of all the subarrays, and just you can say find out the maximum of all the subarray sums you have. Right? This you can do whenever a subarray is you can say formed. You just find out what is the sum of this subarray, and you can maybe collect all the sums of the subarrays and take the maximum of them. But how do you find all the subarrays? That's also interesting. Let's see. How do you go about finding all the subarrays? Let's find out all the subarrays starting with A1. Then let's find out all the subarrays starting with A2. Then let's find out all the subarrays starting with A3, A4, so on and so forth, right? So what are all the subarrays starting with A1? What do you mean by starting with A1? All those subarrays, all those contiguous segment of this array which start with A1. Now 1 is A1 itself, right? One important thing, they are asking for all the non-empty subarrays, right? So you cannot, you have to pick one element in this segment. Okay, so we are only talking about here non-empty subarrays. So one guy is A1 here, fine. What about the guy? A1, A2. Yeah, okay. A1, A2 is also there. Then A1, A2, A3. Okay. Then A1, A2, A3, A4. Yeah, okay, makes sense. A1, A2, A3, A4. So you're seeing what I'm doing. I'm just incrementing one element and then A1 till A5. Right, so these are all the subarrays starting with A1. What about A2? So first will be A2 itself, then A2, A3, right? Then A2, A3, A4, then A2, A3, A4, then A2, A3, A4, A5, right? So this is all the possible subarrays which is starting with A2. Similarly, you can get for A3, then A4 and A5. So all the subarrays starting with A5 will be simply A5 only. Now what do you see? Do you see a pattern here? See, what are total number of subarrays starting with A1? If we count here, 1, 2, 3, 4, 5. So there are 5 subarrays, you can say non-empty subarrays which start with A1. How many non-empty subarrays start with A2? They are 1, 2, 3, 4. 4. So similarly, all the subarrays starting with A3 will be 3. All the subarrays starting with A4 will be 2. Similarly for A5 it will be 1. So what is this? So what are total number of subarrays you have? 1 plus 2 plus 3, 4. So you can clearly see if you had n elements, the total number of subarrays would be 1 plus 2 plus 3 plus so on till n. What is this? The sum of first n natural numbers, which is nothing but n into n plus 1 by 2. In other words, order of n square. So there are you can say n square possible subarrays existing, and we have already seen how to create these subarrays, right? So in a way, I described these subarrays. You can now generate these subarrays as well, right? So you can enumerate all the subarrays in order of n square, or maybe just find the sums in the process of generating subarrays and take the maximum of them. But the problem is this is gonna consume order of n square time, so we cannot do it. But so like this can be implemented very easily. So if you want to see how this can be implemented, is what you'll have to do is exactly how I described the procedure. So for I equals to 1, I can go till n, and then for j, I'll start from I only, right? Because the first subarray that started with ai is ai. So we start from I, and then we go till n, right? So what you can do is maybe you can initialize the sum of I, or you can say the current subarray sum to 0. Okay. Now what you can do is if you want to find out the subarray sum for the current subarray that you have, you will have to simply do si plus equal to array of j, right? And then maybe you can initialize, you can say MSS to a very small value, let's say minus infinitive, because we want to find the maximum subarray sum. So maybe initialize it to negative infinitive, and here you can try to update maximum subarray sum to the max of MSS and SI, the current subarray that you have. And like this is a perfectly fine loop. So what is happening here is, guys, see, what you do is you start with the first guy, right? So let me use a different color. You start with the first guy, A1. So when I is 1, you start with the A1, and then you initialize SI to 0. Then you start your J loop from 2. Maybe let me write it here. You start your loop from 2 till n, right? Till 2 till an. Then at every iteration, you start your loop from I equals to 1, right? So at first iteration, you are going to add A1 to this. Then you have the you have the subarray sum for A1. In the second iteration, you're going to add A2 to this. So you will have a subarray A1, A2. In the third iteration, you will add A3. So then you will have a subarray sum for A1, A2, A3. So on and so forth. So when I equals to 2, you first start with A2, then A2, A3, then A2, A3, A4, so on and so forth, right? So this is a perfectly fine solution. Like this does calculate the maximum subarray sum, but the only problem is its time complexity is order of n square. So you cannot implement it. So if you're going to do it, then what next? I might argue that if this solution was not going to work anyway, then why did I write the pseudocode and explain to you how all the possible subarrays can be enumerated? The reason is because this idea of subarrays, subsequences and all is used extensively in competitive programming. So it pays well to have a fundamental grounding of how subarrays work, and there are all order of n square possible subarrays. Fine. So let's move on to the optimal solutions then. So we want to do something better than order of n square. Okay. Now, how should you approach it then? Now, this is a very common pattern, you can say, like in this subarray based question. The problem was the nested loop, right? So for, you can say, what we are doing is we are trying to generate all the possible subarrays starting with some index. Now, can we get rid of that nested loop, the inner loop somehow? If there was some way to find out, let's say, among all the subarrays which start with A1, which one yields the maximum sum, my job would be easy, right? Then instead of doing n comparison, so you can say running order of n loop, I can just get that in constant time. You don't get what I'm saying, right? So what I'm saying is, let's say we had here A1, A2. So what we are right now trying to do is try to generate all the possible subarrays starting with A1, right? And among them, we will pick, you can say we'll only consider the one which is maximum. So if there was a way that among all the possible, you can say here order of n subarrays starting with A1, I can get the maximum subarray sum among all of them which start with A1 in order of 1, then my job can be easy. Right, so in that case, then since we have n elements, if you have a way to find out maximum subarray sum for all the subarrays starting with A1, then A2, then A3, A4, so on an, then the total time complexity can be order of n. Stay with me for a while, you'll get what I'm saying. But getting a maximum subarray sum starting with the index is not a very easy problem. But if you think in a bit other way, that is there a way to find maximum subarray sum ending at index I? So this MSSS of I am saying that this is maximum subarray sum ending at index I. Is there an optimal way to find that? Right, so we know that one way is to just enumerate all the possible subarrays ending at index I, which will be again order of I, right? So what are the number of subarrays ending at index 1? Just A1. What are number of subarrays ending at index A2? A1 and A2. So we know that we can run order of n loop and find that, but is there a way to do this efficiently? Let's see. Let me write down a subarray here, like array here, so then I'll maybe able to explain in a better way. Let's say we had A1, A2, A3, A4, A5, so on. Let's say an minus 1 and an. Okay, so this is our array here. Now, what I'm after is when I am at this, let's say A4, I want to find out the maximum subarray sum ending at index 4. Okay, now what all are our candidates? Now maximum subarray sum can exist for like A4, like this can be the subarray for which we have the maximum subarray sum, right? So you get the problem what I'm trying to do. I'm trying to find out maximum subarray sum ending at index I among all the subarrays which end at index 4, which subarray yields the maximum sum. So that's what I'm after. Now, like this can be one of the candidate, or one subarray can be this as well, right? One subarray can be this as well, or one subarray can be this as well, right? Or one subarray can be this as well. So how many candidates are there? There are 1, 2, 3, 4 candidates, right? Okay. Now, how do you find the maximum among these? So I am looking after maximum subarray sum ending at index 4, and I have 4 candidates. Okay. Hear me out very attentively. The candidate array which yields the maximum subarray sum ending at index 4 can be formed by either removing all of these guys. So if you remove all of these guys, you will get A4, right? Or by removing just these two guys. So if you remove these two guys, it will be A3, A4, okay? Or by removing just A1. So in that case, the maximum Subarray sum, like the array corresponding maximum Subarray sum here will be A2, A3, A4. Or maybe you remove nothing, right? So if you want to find out the maximum Subarray sum ending at index 4, what are your options? Either remove all these three, okay, or remove these two, or remove this guy, or maybe remove nothing. Now very important, if you want to find out maximum Subarray sum ending at index I, it can be found by you first find the prefix sum till I, right? So from this guy you remove the smallest possible prefix sum. That is, from this guy either you remove from this guy either you remove this, or you remove this, or you remove this, or you remove nothing. In other words, from this part you remove minimum of 0, that is you remove nothing, minimum of 0, prefix sum of 1, prefix sum of 2, 2, so on till prefix sum of I minus 1, right? Simple. You want to find out the maximum Subarray sum ending at index 4. So what you do is, from this part you either remove nothing, or you remove this part, or you remove this part, or you remove this part. Now which one are you gonna remove? You want the maximum Subarray sum, so you're gonna remove the minimum of this. So, and using this idea, we can actually find a optimal solution for a problem. How? If you can just maintain a running minimum, that is as in when you advance through your array, running minimum of this, that is prefix sum of like when you are here, you have the minimum of 0, simply 0, right? So when you're here, you have minimum of 0 and prefix sum of even. When you are here, you have minimum of 0, this part, this part. So this can be easily done, right? You can just update it at every step. So this can be maintained as a running minimum, and prefix sum of I can also be calculated on the fly, or maybe you can pre-compute it, but there's no need for pre-computation. So this both, for every I belongs to 1 to n, I'm talking about 1 based indexing here, guys. For every I from 1 to n, we can find the maximum subarray ending at index I in constant time. It says in just order of n time, we can have the maximum subarray sum, right? If we can have the maximum subarray sum ending at every possible index in the array in constant time, we have order of n solution. Interesting, right? So how would the solution look then? Let's try to write the pseudocode here. What I'll do is I'll first initialize the maximum subarray sum with the maximum subarray sum ending at index 1 only, right? Then I'll start from index 2. So maximum subarray sum ending at index 1 is simply array of 1, right? Or maybe just use the terminology like even, right? And what do we need? We need to keep track of prefix sums, right? So prefix sum of I. So prefix sum of I is a prefix sum like till the first guy is simply even, so that is even, fine. But we also need this concept of prefix sum mini, right? So maybe let me just call it prefix sum mini. That is whenever you are at this guy, you need minimum of 0, this portion, right? So prefix sums basically. So we also need that notion. So let's initialize prefix sum of mini. So when you are the second guy, this would be minimum of what? 0 and even, right? So 0 and the prefix sum till the first guy. So this should be right now minimum of 0 and even, right? Fine. And then I can just run a loop. I can go from I equals to 2 because I already have computed the maximum subarray sum. You can say ending at index 1 from I equals to 2 till n. First things first, let's update our prefix sum of I. What is the prefix sum ending at this index? It is simply, you can just add ai, whatever you have. Then what is the maximum subarray sum ending at this index? It is from the prefix sum, maybe let me write in different color. From the prefix sum ending at this index, you just subtract the minimum of 0, p sum of I, p sum of 2, so on and so forth, minus ps of many. That is minimum of all the prefix sums from 0 till I minus 1. Now what is prefix sum of 0? It is simply 0. It is the part where you don't remove any element, right? So there is no 0 guy, but that's what prefix sum of 0 means. And you update the maximum prefix sum. So maybe what you can do is you can take maximum subarray sum to be max of this part. So this is a maximum subarray ending at current index, and whatever the maximum subarray sum is now is present till now, and that is that. And then you will have to update, right? So what you'll have to update? You will have to update prefix sum mini, right? Because when you move the next guy, you want to like keep track of the running minimum, right? So now you want to actually update. So how are you going to update it? You are going to write ps mini to be equal to, so this should be minimum, right? So minimum of whatever the current value is, and prefix sum of I, right? So simply when you move ahead, what you'll do is you will update with whatever the current minimum is among this. It can be either this or prefix sum till this part, right? So that's the idea. So that's how we do it. And of course, after this loop ends, you can print the maximum subarray sum, right? Now, time complexity of this approach, like this is the pseudocode is done, right? It's a perfectly valid pseudocode. Time complexity, I guess we have already discussed. It's simply order of n, because for every index, we are just finding maximum subarray sum in this constant time, right? So these are all constant time operations. Space, we are not using any extra space. Even all the prefix sums are maintained in a constant time, like constant space variables. Space complexity is order of 1. So I mean, yeah, that was about the approach. If you have understood the video till now, the approach that I have discussed till now, please comment understood in the comment section of the video right now, and we can move on to the dry run, right? So let's do a dry run on this example. Now what do we do at each step more concretely? First thing is we find out the prefix sum ending at index I, right? So that's what we do first, right? Prefix sum ending at index I. Then we find out the maximum subarray sum ending at index I, right? So this portion, and then we update MSS, right? Then we update the maximum subarray sum, right? The global maximum subarray sum, and finally we update the minimum prefix sum, right? So we update the p sum mini, right? So these are the 4 steps we take at each step. Fine. So initially, what is MSS? MSS maximum subarray sum is actually initialized to -1. Simple, is initialized to -1, and then we initialized prefix sum of I. What do we initialize prefix sum of I to? A1. So it is -1. And what is prefix sum of mini? Prefix sum of mini. Now what we do is we initialize it to minimum of 0 and -1. Why? Because when you go at the second guy, we want the minimum of prefix sum from 0 till 1, till I minus 1. What is prefix sum of 0? It's simply 0. It is just about the case where we are not removing anything, right? So this is minimum of 0 and -1. So that is of course -1. So all 3 are initialized to -1 here. Okay. So this also makes sense. So what are these values? Maximum subarray sum ending at index 1 is actually -1, right? And prefix sum till 1 is also -1, and the minimum prefix sum till this part is also -1. So this makes sense. Let's move ahead step by step. Let's come to this guy. First thing, we update the prefix sum of I. So -1 plus 3. So it will become 2. So prefix sum of I, so this step is done. Prefix sum of I becomes 2. Then we find out the maximum subarray sum ending at index I. Now what is MSS of I? It's simply prefix sum of I. Prefix sum of I, that is sum of all the elements till this part. You just remove the smallest possible guy till here. So 2 minus, what is that prefix sum of mini? -1. 2 minus -1. So it turns out to be 3. So is 3 greater than the maximum subarray sum? So we have done this part. Now we are here updating the maximum subarray sum. Is 3 greater than MSS? Indeed it is. So we are going to update it to 3. notice what happened. The maximum subarray sum ending at this index is actually 3, right? Because you had two options, either -1 or 3, but you decide to choose 3. And how did you find 3? From this portion, you removed the smallest portion from 0 till 1. That's why MSS till this MSSI of 2 is actually 3. Makes sense. So that's about it. So this is 3. Okay, fine. The last step, update the prefix sum mini. Now you have two options, like you want to update the prefix sum till this portion, minimum prefix sum till this portion. Now what is the original value of prefix sum mini? It is -1. So it will be minimum of -1, and what is the prefix sum till this, which is actually 2. Of course you will keep -1, right? So you'll not update it. Fine, move ahead. Let's move ahead. So this is done, this is done. Now let's come back. So first things first, update prefix sum of I. So it is 2 minus 2, which is 0. Okay, prefix sum of I is 0. Then find the maximum subarray sum ending at index I. That would be what? It would be prefix sum at this portion 0 minus the minimum prefix sum till this portion, which is actually -1, right? So 0 minus -1, right? So which also turned out to be 1. Now indeed this is the case. The maximum subarray sum ending at index 3 is indeed 1, which is this portion, right? So what did you do? From this portion you subtracted the smallest possible sum, which was actually -1. Fine. So that's what you did. So maximum subarray sum ending at this guy is 1. Now the next step is try to update the maximum subarray sum. Which one is higher, 1 or 3? 3. So we are not going to update it. Then update minimum prefix sum. So try to update the minimum prefix sum till this portion, which is equal to whatever the current value is. Remember, we are maintaining the running minimum. Current value is -1, minimum of -1, and 1. Like not 1, -1 and 0. Of course, -1 is smaller, so we'll keep -1 and move ahead. So these 4 steps were done. First step, update the prefix sum till this part. So we are here, right? So update the prefix sum. So now the prefix sum of I actually becomes 5, right? So the sum of all the elements till here is 5, which is indeed true. So we did the first step. Now update, like find the maximum subarray sum ending at index 5. So if you want to find maximum subarray sum ending at index 5, from the prefix sum you subtract the lowest possible prefix sum among indices 0 till 3. So what is that thing? 5 minus -1 is turned out to be 6. Okay, now try to update maximum subarray sum. Which one is higher, 3 or 6? 6. So update it. Indeed, if you see here, the maximum subarray sum ending at index 4 is actually 6. This portion, right? So 5 plus 3 -2. Then we will try to update the prefix sum of mini, but it will still stay -1, right? So then we'll move ahead. First thing we do, we update the prefix sum of I, which is actually 5 plus 3, 8. Then we calculate maximum subarray sum ending at index I, which turns out to be 8 minus -1. That is, from this portion you remove the smallest possible prefix sum, which is -1 here, and this actually turned out to be 9. That is 9 greater than 6. Indeed it is. So update it to 9. Now the rest of the operation doesn't matter, and this is your maximum subarray sum. So I hope you have got the dry run, and that's about it. We can move on to the code, but I want to discuss one more approach to this problem. It will be a major injustice to the maximum subarray sum problem if I don't discuss which we call Kathan's algorithm. And like this is, you can say, the algorithm that like at least the interviewer expects when they present you this problem. And this is also a very interesting problem, but I didn't discuss it at the first because the idea that it gives is a bit complicated. Like frankly, you won't be able to come up with it on the go. That's why I discussed the more intuitive approach first. Now, how does the Kathan's algorithm work? Now, it also relies on the fact that we want to find the maximum subarray sum ending at index I efficiently. So what the Kathan's algorithm says is the maximum subarray sum ending at index I is actually equal to max of area of I or maximum subarray sum ending at index I minus 1 plus area of I, right? So This is what Kathan's algorithm asks you to do. In other words, what this guy is saying is, if you have, let's say, this array, and you are here, you want to find the maximum subarray sum ending at this index, you have only two arrays to consider. Either you consider this guy, that is, this guy will yield you a subarray sum of array of I, or to the subarray which is yielding the maximum sum ending at index I minus 1, you append this guy. Because any which way, you are trying to find the maximum subarray sum ending at index I. So the last guy has to be array of I. But what this guy is saying is, you only consider two arrays. One is array of I, single guy, or to the subarray which yields the maximum sum ending at index I minus 1, you append array of I. If you just think a little bit, this is same as what you have done. If you're not able to think, don't worry, I'll give you a proof that this is indeed actually true. But what this hypothesis helps us to do is, again we can calculate, you can say, the maximum subarray sum in order of n. Because this portion for each I from 1 to n can be calculated in constant time. Because now you only have two subarrays to consider at index I. One is the guy itself, or to the subarray which yields the maximum sum ending at index I minus 1, you just append array of I. Fine. So let's see how can you prove this, like whether this argument is true or not. Once you can prove it, the implementation is pretty straightforward. You can see the code and pseudocode for it as well. But first, let's prove this. The proof is actually very simple here. Like, it's much simpler than you think. Let me show you the proof. See, what I'm arguing is, let's say we have an array here. So I guess the boxes will help here a lot. It will actually simplify the proof. If I can draw the box correctly, it will help. Okay. Let's say someone is asking you to find the maximum subarray ending at index I. Now what Kathan's algorithm is arguing is, you consider either this array, this subarray. Now you know the subarrays ending at index I will be I. We have already discussed it so many times in this video. So, but Kathan says you either consider this array, or let's call the maximum subarray ending at index I minus 1. Let's say without loss of generality, it spans from this guy till I minus 1. Of course, the last guy will be I minus 1 only, because this is what? This is the subarray which yields maximum subarray sum ending at index I minus 1. Fine. So let's call this guy as MSS of I. So without loss of generality, this is how it looks. It starts with this guy, and of course it has to end at I minus 1. So that is clear. Then what? Now, let's assume this is not the case. Kathan says we have only two candidates. Either pick array of I, or to the maximum subarray, like to the subarray which yields the maximum subarray sum for index I minus 1, you append array of I. Right? You append the same portion. Now let's argue that no, there is one more candidate. There is at least one more candidate existing. Okay. So I'm trying to bring a contradictory proof here. So what I'm saying is, Kathan is wrong, and there is one more subarray which ends at of course at index I, because it has to end at index I. So it must end at index I, but it yields a sum which is greater than these two subarrays. Okay, so this is my hypothesis. I don't know which this sum is, but let's just call this sum as x. Okay, let me name this portion. So let's just call this as y, and this all portions are same. So this is simply array of I, this is array of I, and this is array of I. Okay, so Kathan said you only had two options to consider, but I'm arguing no, you are wrong. There is one more subarray which is yielding maximum sum. So what I'm arguing here is, this x plus ai is actually greater than ai, and x plus ai is actually greater than y plus ai. This equation is fine. We don't have much to see here, but if you see at this equation, what this equation says is x plus ai greater than y plus ai. So if you cancel ai on both the side, you are saying x is greater than y. You are saying that this portion is actually greater than this portion. What is this portion? This is a subarray ending at index I minus 1, right? So you are saying we have a subarray which ends at index I minus 1, and it yields a sum greater than y. But I already told you we had a maximum subarray sum ending at index I minus 1. So that's a contradiction, right? If some subarray has to exist apart from these two, this y cannot be maximum subarray sum. This is a contradiction. I already assumed that this is a maximum subarray sum. Why? Because if you had some other array, this portion is same, but this portion has to be greater than this. But if this portion has to be greater than this, then you don't have a maximum subarray ending at index I minus 1. So that's why Kathan is indeed right, and the maximum subarray sum ending at index I minus 1, we have only two candidates, area of I or MSS of I minus 1 plus area of I. Now that's Kathan's algorithm, and I can write the pseudocode for this, and we can wrap up this video then. I can discuss the pseudocode for Kathan's algorithm, but I guess we have covered enough ground by spending so much time in the prefix sum based question. You will understand the implementation of Kathan's algorithm on the fly, right? Because it is almost similar if you observe. Effectively, we are trying to find the maximum subarray sum ending at index I in constant time, right? So it will go on the same lines here. See, I've taken the array input here, int n, and vector of ints. Vector of ints will work because all the elements are in range of integer. It's just when we try to add something, we'll have to do in long. That's why all the longs are here. Then I'll first initialize the maximum subarray sum to be area of 0. That is the maximum subarray sum ending at the first guy is actually equal to simply the first guy itself. Then this MSSS of I. So this, for a current iteration, at the start will have the maximum subarray sum ending at index I minus 1. So when we start from 1, we need to have the maximum subarray sum ending at index 0. When we have I equals to 3, at the start of the loop, we should have maximum subarray sum ending at index 2, right? So clearly, we have two candidates for a value of I, either area of I, or to the maximum subarray sum ending at index I minus 1, you just add area of I. So you take maximum of this. You might be like scratching your head, why did I do one LL here? It is because like max is not gonna let you can say do the maximum if both of them are of different types. Like if this is an integer and this is a long, it's gonna return an error. So it's just a little bit of C++ nuance. So when I do this, I'm just converting the area of I explicitly to a long. Or in other words, you can just take a vector of longs and that would work as well. And fine. So after we have found the maximum subarray sum ending at index I, we can just update the global maximum, right? And after this loop ends, we have the maximum subarray sum, right? Time complexity order of n, right? And space complexity is also order of 1 because we just run one loop and in each one of them we just do a constant time operation. Fine. Let's move on to the prefix sum based approach then. First things first, array input, fine. Then we initialize the maximum subarray sum to a ARR of 0. Then prefix sum of I, p sum of 0, simply area of 0. Then this is important. We want the prefix sum from nothing to I minus 1. So in this case, it will be 0 to ARR of 0. And then we go from 1 till n, that is we go from second guy till the last. First find the prefix sum. From that, if you want to find the minimum maximum subarray sum ending in index I, from the prefix sum you subtract the minimum prefix sum just before it. Update the global maximum subarray sum and then update the prefix sum mini for the next guy. And then we can print the maximum subarray sum. And time complexity again here is order of n, space complexity is also order of 1. Now as an interesting exercise, what you can do is you can try this question, Yarrick and array from CP31 sheet. I guess it was from 1100 rated question. And you can test your knowledge that you have learned from maximum subarray sum. So you'll see like this logic is applied there. And yeah, I mean that was about this video. I guess it was a pretty long video. I hope you got something out of it. You liked it. If you did, please give it a thumbs up. And I'll see you in the next one.